Good, now let's get to the reason for why we introduced kmaps in the first place, because pretty much everything I've shown you so far you could do almost as easily using just Boolean minimization, and certainly wouldn't be worthwhile to introduce this whole new concept just to minimize functions as we've seen them before. The main power of kmaps really comes in the context of using don't cares. So don't cares essentially are these x's in the kmap, so x's in the truth table. And we'll see in the next slide where these x's come from. But the basic implication is that if you have an x here, you do not care whether it's a 0 or a 1. And what you want to do is you want to choose the value of every given x in such a way that it makes it that the function you get at the end is the smallest possible function. Okay? So in these three kmaps, I've essentially have the exact same function, but I just want to make different choices for x to demonstrate that it actually matters what you choose, right? So let's do in the first example, let's just say we're picking all the x's to be 0. So I'm going to put a 0 here, a 0, and a 0. So now the circles that I can draw, so there's one here, this one, hopefully you notice, can be packed into a circle that sort of wraps around, and that's actually all you need. So all you have is two circles, and your function in this case is the bigger circle here is not a d, and then the smaller circle here, it's not c, d, not b, or not b, but I say not c, d. Good. So that was one choice. Here, let's make the opposite choice, and let's say that we pick all the x's to be 1. Okay, so now I can draw this circle here. Okay, to cover these ones, I can make a circle here. And then I also have to get this circle up here to cover the one up here, and this circle down here. Okay, so the total function here is not c, d, or not a, d, or a, b, not c, or c, not a, b, c. Okay, so essentially by making this second choice, the function actually became bigger. So in this particular function, choosing x to be 1 is a less good choice than x equals 0. But the question now is x equals 0 actually the best choice? And the answer is going to be probably not. What you should do is really treat the x as a don't care and just pick it to be a 1 when it's convenient, and pick it to be a 0 otherwise. And whether it's convenient or not is essentially determined by whether it allows you to make an existing circle bigger or not. Okay, so let's look at this. So here, this is the circle we've been drawing every time. In the first version, we picked this x to be 0, and we kind of had a circle that just wrapped, around these two ones. In the second version, we picked this to be 1, and we were able to make this big circle here. But now, with this choice, we've essentially covered all the ones that were initially there. So it actually is convenient to make these two equal to 0, so I don't have to circle them. So I don't have to add anything else to my function. And if I make this choice, so just this x a 1 and the other ones to be 0, then my function is, again, this circle here, not a d, it's the 2 by 2, or, and this is d, not c, d. Okay, so you can see that this function is more compact even than the one we got when we chose x to be 0. So this is how you essentially treat don't cares. You pick and choose whether you want to make them 1s or 0s depending on whether it allows you to essentially make bigger circles around ones that you have to cover to get your complete function. Okay, so now the question really is where do these x's come from? How do I encounter them? And so this is where I want to do this example. Again, so the first thing we want to do for this example is essentially write down a truth table. And this is maybe not totally trivial, so I would recommend that you think about this for a couple of minutes and actually try to fill out this truth table yourself. Okay? So here's how I would do this. So you have two players, player 1 and player 0, and they each can input rock, paper, or scissor. So I have player 1, player 0, that's 4 possible inputs, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1. Then 0, 1, 0, 0, 0, 1. Okay, 1, 0, 0, 0, 0, 1, 1, 0, 1, 1. And then, of course, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. Okay, that's all the possible combinations of inputs. Then on the output side, okay, what do you have? So there's two types of outputs. There's the win and there's the tie. We say that for a win, we output the winner's ID. So if player 1 wins, we output a 1. If player 0 wins, we output a 0. If there's a tie, we output true if it's a tie, and if there's no tie, we output false. Okay, so in this first row, right, both players choose rock. So both put 0, 0, and obviously that's a tie. Now, the win, well, we actually don't care what happens here, right? We say if tie is true, I'm just going to ignore the win column. I can put a 0 there, I can put a 1 there, it doesn't matter, I'm not even going to look at it. I'm just not going to count it. Okay? In the next combination, so 0, 0, first player, or player 1 plays rock, player 2 plays paper, so player 2 should win, or sorry, player 0 should win. There's no player 2, and we don't have a tie. In the next case, rock beats scissor, so 1 wins, no tie. Here you get a bunch more X's because essentially there's no, sure you can input 1, 1, but it doesn't correspond to anything that's allowed within the game. So we're just going to ignore, if one or both of the players choose to put 1, 1, we're just going to ignore that. Okay? So now you can fill in the rest of this truth table sort of following the same logic. So you should get 1, X, 0, X, 0, 1, X, X, and then a bunch of X's down here. And then this column is 0, 1, 0, X, 0, 0, 1, X, and a lot of X's. Okay, so you could refer to this X here as an output don't care. And you could, for example, refer to these as input don't cares. Again, because here you're essentially playing illegal input combinations, so you're just not going to look at what the output is in the first place because it doesn't make sense within the game. Here it's because if there's a tie, the win, nobody wins, and so you can put whatever there, it's just not counted. Okay, good. So now, actually this previous example is quite important because you, in your lab, you're sort of going to see something very similar where you essentially get to write down a truth table where you have several combinations of inputs or outputs. Essentially you get to put an X. Good. Once you've done this, once you've sort of completed the truth table, the rest actually becomes pretty standard. Because what you're going to do now is you're essentially going to fill in the kmaps, just copying what you had on the previous slides. I'm just going to do this quickly, but I recommend that you do it yourself. So the truth table is, or the kmap is x0, x1, 1x1, x, x0, x, 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 0, 1, x, x. This is for win. Okay. So now you get to choose the value of x, as we've seen before, to be whatever you need it to be. And in this particular case, so you have a 1 up here. You want to make the maximal circle that sort of covers that 1. So it's clear that expanding this from just a 1 by 1 to a 2 by 2 would be helpful. And this is the circle B, not C. Then you have to look at this one here. And again, you can make a 2 by 2 circle by choosing all of these x's here, the 3 x's, to be 1s, and that is A, D. And then you only have one left here. And you could, again, or you can choose another 2 by 2 circle that sort of wraps around. And this is not B, what is it? Not BC. Okay. So here you found that win is equal to AD or not BC or B not C. Okay. So same idea over here. If you just fill in the kmap for tie, first you get 1, 0, x, 0, 0, 1, x, 0, x, 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 x. Good. And so again, you have to pick your x's anyway, or you get to pick them any way you want. Well, you can start with this one here. There's really nothing you can do. It's just surrounded by zeros on all sides. On the other hand, this one here, you can make a 2 by 2 circle to cover it. Similarly, this one here. And I think that's all there is. So this circle up here is not A, not B, not C, not D. This one here is BD, and this one here is AC. So tie is AC or BD, or not A, not B, not C, not D. Okay, good. So now I think hopefully this example has sort of given you an idea of why kmaps are powerful and how to use them. And again, I think the most interesting application for kmaps is in this context of where you have a certain number of don't cares in your truth table, and you kind of need to figure out what to do with these don't cares. And visually in the kmap, it's sort of easy to see whether you want to choose a given x to be a 1 or a 0 in order to get a minimal function. While if you try to do the same thing just by looking at the truth table, I think it'd actually be quite hard.